bajo la dirección de Ilya Ittenberg en geometría algebraica real, y durante su doctorado fue que empezó a desarrollarse la geometría tropical, siendo la Escuela Rusa de Geometría Algebraica Real uno de los pilares de este desarrollo. De esta manera, desde sus inicios, Erwan ha estado involucrado en los avances de esta nueva área de las matemáticas. Ya doctorado, realizó estancias postdoctorales en el Institut Thomas Planck en Bonn, en la Universidad de Toronto y en el MSRI de Berkeley. Sus trabajos más conocidos abarcan geometría algebraica compleja, real y tropical, y geometría enumerativa, de lo que nos va a hablar el día de hoy. Actualmente cuenta con más de 30 artículos de investigación y tiene varios textos para público no especializados, y uno de ellos ganó un premio, uno titulado Un poco de geometría tropical. La relación de Erwan con México es estrecha. Desde el año 2009 ha realizado estancias de investigación de manera regular, tiene artículos de investigación con matemáticos mexicanos, ha impartido minicursos especializados en la UNAM, ha organizado eventos académicos en nuestro país, y su primer estudiante de doctorado es mexicano y está por aquí, Cristian Garay, así que además tiene un hijo mexicano. Además de la relación académica, en México disfruta de la comida, del baile, la naturaleza y muy particularmente de la lucha libre, así que hasta tiene un nombre de luchador. Así que pues me da muchísimo gusto presentarles a Erwan, y pues de entrada nos disculpamos de que la plática va a ser en inglés, esperemos que todos entiendan, y si no, pues anímense a preguntar si hay algo que de plano no están entendiendo. Bueno, pues gracias. Bienvenido, Erwan.
Muchas gracias. Es un gran placer y un gran honor de estar aquí. Desafortunadamente no puedo dar una plática en español, entonces voy a hablar en inglés. Disculpa. Okay, so at least in English, I will be able to make less grammar mistake. So the topic of my talk is enumeration of real curves, and I will also talk about complex curves and tropical curves, and try to mix these three things. So let's. Okay. So let's stop. Okay. So wait. So does it work? No, it doesn't work. Okay. No, wait. It goes too fast. So what? Oh, okay. So let's try. I have no idea if it's me who does something or if it's you. Is it you? Okay. So let's start with a warm-up to see what kind of problem we are going to deal with. So let's take 2 points in the plane, and let's try to compute how many lines pass through these 2 points. So there is 2 strategies at least. So the naive one, so you take the 2 points and you trace the line, and then you count it 1. Okay. So and there is also the more developed strategy. So maybe So more developed strategy. So you say that okay. So what is a point in the plane? It's a line in the dual plane, and yeah. So then your 2 points correspond to 2 lines in the dual plane. 2 lines intersect in 1 point, and this point is the line. So the answer is 1. So it's kind of very developed strategy to solve this problem. Okay, but depending on your taste, you can choose one or the other. Let's try to compare this two strategy for Okay. But really, it doesn't work here? No. Ah. No. Well, okay. So, yes, please, next. Well, okay. So, what can we say? So, the naive strategy, what is good is that the line is constructed. Please. Yeah. Okay. So, once you constructed your line, you can do whatever you want with this line. For example, you can count. Why not? So, this is the nice aspect of this strategy, but there is some drawback. This is not very efficient to solve a more general problem. So it's nice to count lines through 2 points, but in general, so for example, how many rational complex curves of degree 20, whatever that means, it's not very important, pass through 59 points in the plane. Okay. You can try to construct all these curves and then see how many you have. What about the developed strategy? So the developed strategy is, the nice thing is that it's completely, it seems very difficult for the case of lines, but it generalizes to a lot of situations. And the strategy is always like that. So you start with your problem. Okay, so before we wanted to count lines. So then you construct some moduli space that parameterizes all the objects that you are interested in. So before it was the dual plane, which parameterizes lines in the plane. So in the previous situation it was compact, but usually it's non-compact, so then you have to compactify it, and then you do some intersection theory, and then your problem is solved. Okay, so it sits in a very general strategy, which gives you an amazing success. So with this, you're able to compute a lot of things. So for example, we can compute, please, that this number of rational curves is this number. Okay, it's more than the number of particles in the universe. So if you wanted to use the naive strategy to compute this number, then it will have taken you forever. Okay, so it's really great. It works amazingly. So of course, when I tell you this strategy, okay, you take the moduli, you compactify, you intersect, it's more or less like when you have a problem with your computer and you ask to some computer scientist how to solve it, and he says, yeah, just you do this, you install this program, run blah blah, and it works. And then you go home, you try to do it, and nothing works. Okay, so here it's more or less the same story. So you still have a lot of work to do at each step, usually. But nevertheless, this is how it goes. But you also have some drawbacks with this strategy, and please. Yeah, so it works so well that any problem that you cannot solve with this strategy looks a bit suspicious, and maybe you will think that it's not interesting. Okay, so that's a problem when we have a very powerful method to solve a problem, is that we are not interested in the problem we cannot solve. Okay, so we like more the method than the problem. And so, for example, please. So this is the answer that you can get from someone very well-known in the field, that you want to compute some numbers that nature gave you to compute, okay? And the answer is, no, your number is not natural. Yeah, but that's the problem I have. Okay, so that's the drawback of the method. So now I would like to specify on the enumeration of plain rational curves. So let me, please, thank you, explain you this problem. Okay, so what is a rational curve? So a rational curve in the plane, this is given by a map. Okay, so I take 3 polynomials, P, Q, and R, without common factors. They are of degree D in one variable, and I look at the map that goes from C minus the 0 R to C2, which is given by the fraction P over R and Q over R. Okay, and so this is a rational map, please. So it's better to look at it from the projective point of view. So it corresponds to a map from CP1, which is C when we add infinity, and CP2, which is C2 when we add the line at infinity. And with this perspective, so the map can be written in a more symmetric way. But if you don't know what is projective plane and projective line, it's not a problem, I think. Okay, so this is a rational map, and please, so the image of such a map is called a rational curve. So it's the image of the line, of this map, which is a rational curve, not the map itself, okay? So for example, you can reparameterize C, make a change of coordinates, and you will have the same image, but a different curve. Please, okay. So what is the dimension of the space of rational curves? It's easy to compute. So I need 3 polynomials of degree d. So each of them is given by d plus 1 monomials. So we have 3 times d plus 1. But they are defined up to some common multiple factor, because if I multiply p and r by lambda, I got the same rational function, so I have to subtract 1. And I can also make some change of coordinates in C, and it's 3 degrees of freedom, so I have to subtract 3, and so the answer is 3d minus 1. So if you look at the space of rational curves of degree d in the plane, the dimension is 3d minus 1. So now you can, as we did with the space of lines, so if d equal 1, okay, the space of lines, the answer is 2. So the space of lines have dimension 2, and that's what I did before. I fixed 2 points, and it was enough to have finitely many lines that pass through these points. And here it's the same. If I fix 3d minus 1 points in the plane, I expect to have finitely many rational curves of degree d that pass through these points. Please, can we have next slide? Thank you. Okay. And this is indeed what happens. So I fix some degree, I take some generic configuration of points. So I don't want to detail what means generic. It just means that if you have a configuration of points which is not generic, just move it a little bit and it will become generic. And then I look at all curves of rational curves of degree d that pass through these points, and I have finitely many of them, and I denote this number by this GWCP2 of D, so it's known as a Gromov-Witten invariant of CP2. Okay, and it turns out that this number does not depend on the points you choose. Okay, so it's independent. You can choose any configuration of 3d minus 1 points. As long as it is generic, the number of curves is the same. So this is like when you look at polynomials in one variable. Okay, so the number of roots of a complex polynomial in one variable only depends on its degree and not on its coefficients. Okay, so here is the same. The answer just depends on d, and it will not depend on the points which can be regarded as coefficients of the problem. Okay, so this number have appeared since centuries, and they have gained some. They were very fashionable in the 90s because some physicists were very interested in these numbers. So, and for example, maybe please, yeah, let's take some example. D equal 1. The question is how many lines pass through 2 points? The answer is 1. Please, yeah, please again. Okay. So we know how to compute one of these Gromov-Witten invariants. We also know how to compute another one. So please, for d equal 2, it's how many conics pass through 5 points. And this is an exercise in linear algebra. And again, the answer is next, please. Next. Yeah, so it's 1. So through 5 points in the plane, you have only 1 conic. So it seems that this number are very boring. It's 1, 1. So by recursion, the next one should be 1. But it's not. So starting from d equal 3, now it starts to grow. And it grows very fast. So these numbers are not so easy to compute, but Kontsevich in the 90s gave wonderful formulas for these numbers. Next slide, please. Okay, so he said that, okay, don't try to remember this formula. It's not the point, but it's very nice. So there is a very elegant and a short recursive formula for these numbers. And if you know just that through 2 points pass unique lines, okay, which we did at the beginning, then you can compute all of those numbers. Very nice. And please, next. So here are the first values of these numbers. So degree equal 1, we have 1 line. D equal 2, we have 1 conic. And degree equal 3, this is the first interesting and non-trivial case. We find the number 12. And so on. And so you have degree 20 that we were talking about a bit previously. So I don't know. So for d equal 1, I think the answer was known maybe by Cro-Magnon men. Okay, so very long time ago. Degree 2, at least the Greek knew the answer. Okay, I'm not a historian of science, so. Degree 3, I think it had been computed for the first time in the 19th century. And degree 4, it has been computed by Zeuthen at the end of the 19th century. So you see that to go from d equal 1 to d equal 4, it takes from Cro-Magnon to end of 19th century. So it's very difficult problem. It's not easy to compute. And then in the 90s, Weizsäcker computed solve the d equal 5 case, okay, and so then Kontsevich arrived and said, okay, but no, you have this very nice formula and you compute all you want. So it was really an amazing result. Okay, next slide, please. Now, I would like, so this was to enumerate complex curves, okay, and so the situation was quite boring. As soon as you fix 3D minus 1 points, the number of curves that pass through these points, rational curves, is always the same. So maybe this number is difficult to compute, but it's boring because it's always the same. The situations over the real is completely different. So now I do the same, but I'm interested in real curves and real points. So I take 3D minus 1 points in RP2, or if you want in R2. And now I look at the set of real rational curves of degree d that pass through these points. So by real curves, here I mean that, remember, a rational curve is defined by 3 polynomials. So here, a curve is real if the 3 polynomials are real. Nothing more. And then I look at this set. Please, can you... okay, and now the first constatation is that the cardinal of this set now depends on the number of points. So it's like if you look at polynomials in one variable, okay, we know that the number of complex roots only depend on its degree, but if you have a real polynomial, its number of real roots now depends on the coefficients and not only on its degree. And here it's the same problem, now that the number of curves, number of solutions will depend on the 3D minus 1 points I have chosen. So then I have this, okay, can one say something intelligent about the possible cardinal? Please? Yeah, so one easy lemma. So the first one says that the number of real curves is always less than the number of complex curves. Okay. Real numbers is a subset of complex numbers. And also that the number of real curves is equal to the number of complex curves modulo 2. Like the number of real roots of a polynomial in one variable is equal modulo 2 to its degree. This we know. We have the same situation here. And can we say something more intelligent? For example, two questions. Can you always find a configuration of points such that all the curves are real? Or on the opposite, can we find a configuration of points such that we have the minimal number of real curves. That is 0 or 1, depending on the parity of the number of complex curves. So these are quite natural equations, and the answer is wide unknown. So at least in the first case, for the first question, I have no idea in general. So starting from degree 4, I think no one knows if you can find a configuration of points such that all rational curves are real. But for the second questions, somehow surprisingly, we have an answer, and the answer is no. Usually, you cannot find such a configuration of points. So, and the first example was been given by Kharlamov in the 90s, so for different purposes. And he proves, so remember, so the corresponding Gromov-Witten invariant is 12. And he proved that the possible cardinals for the number of real curves is 8, 10, or 12. Okay? So he said that in the case of the first question, the answer is yes, in degree 3. But this shows something very amazing. Okay? You have non-trivial lower bounds. You cannot have less than 8 real curves independently of the points you choose. That was quite surprising. And what is the idea of the proof of Kharlamov is that you have two kinds of rational real cubics. So a rational real cubics in the plane has so one double point, as you see, but you have two kinds of them. So either you have two real branch, you see, that crosses in the plane. This is the first cubic, or you have kind of solitary points. So here are two explicit equations, so you can compute that, you can check that my pictures are accurate. And what Kharlamov discovered is that if you count the first curve with sign +1, and the second type of curve with sign -1, then you always obtain 8. So this is the origin of the 8, which is here. And this observation by Kharlamov that he made for some other purposes, has been generalized by Velchanger in the beginning of 2000, and he proved the following: that you fix your 3D -1 points, you take all the rational curves of degree 3D -1 that pass through this point, real one, and you count them, but not 1, 2, 3, 4, 5, like in the complex case. Now, sometimes you count curves with +1, and sometimes some curves with -1. Okay? And what is the recipe to know what is the sign of a curve? It's exactly like in the case of cubics. It depends on the parity of this solitary node that you see in the real plane. So this is a very simple way to define the sign of a curve, and the amazing theorem is that it gives you something which does not depend on the 3D minus point you took. Okay? And so, of course, just because, okay, so these are called Velchanger invariants, and they are denoted by W, the letter W. And just because we counted curves not 1 plus 2, 1 plus 1 plus 1, but 1 plus -1 plus 1 plus -1 plus -1, and so on. So the absolute value of this Velchanger invariance is always a lower bound for the number of real curves, whatever the configuration of points is. So, if this lower bound is 0, we did not make a huge progress, okay? It was just a very complicated way to define 0, but it's not 0. That's the main thing. So here are the first value of this invariant. So we see that for degree 3 we have this 8 that we talked about before, and then you see that it's non-zero and it grows quite fast. And actually, there is a theorem that in logarithmic scale, thank you, in the logarithmic scale, the number, so this Velchanger invariance grows as fast as the number of complex curves, which is also some kind of very surprising result. And this asymptotic is a 3 log D. in the logarithmic scale. So this was the story up to 2004, and so to compute this Bell-Change invariant, it's also a non-trivial task. And the first way to compute these numbers were by tropical geometry, and which was invented more or less at that time. So let me talk a little bit about tropical geometry and tropical curve, and try to play the same game, but now with some kind of other objects, fancy objects. Okay, here are some examples of tropical curves in the plane, before giving any definition. So this is kind of, okay, it is some pictures. Okay, what can we say? So, a tropical curve is some piecewise linear graph in the plane. And so the first one, the black one, is a tropical line. The second one is called a tropical conic. The third one is a tropical cubic. And the three tropical curves at the bottom are also tropical cubic. So when I say tropical line, tropical conic, tropical cubic, that means that I have a notion of a degree of a curve. Okay, so here the degree, you can see that, so it's the number, so I have three directions where my curve goes to infinity. I have the direction -1, 0, the direction 0, -1, and the direction 1, 1. In all my pictures, I have these three directions at infinity. And the number of rays that goes to infinity in one direction, so is what I call the degree of the curve. Okay, so a line, I have one ray in each direction, conic 2 rays, and cubic 3 rays, and so on. Okay. Okay, maybe I should now define what is a tropical curve. So it's a very simple and combinatorial object. So what is a tropical curve in R2? It's just a piecewise linear graph that satisfies three conditions. So the first one, each edge has a weight, which is some natural number. Then each edge is also contained in a line of R2 which is defined over Z. So it cannot be, so it has a rational slope. So it cannot be any line. Okay, it has to be defined by some equation over Z. Okay, and each vertex, so this is the main point of the definition, satisfies the balancing condition, which means that it's like the Kirchhoff law in electricity. So everything that goes in is equal to what goes out. So this is it. So at each vertex V, you have this condition. So to each edge, we know that since the edge is contained in a line with equation over Z, we have a directing vector which is defined over Z, and we take the smallest one. So it's called a primitive one. So for each edge, we take the smallest, so the primitive integer vector that goes out of V, and we multiply by the weight. And when we add all that, we get 0. So if you want, imagine that at each edge, each edge is a rope, that someone is pulling the rope with force the primitive, with force the weight, okay? So the vertex doesn't move. No one wins. Okay, so any piecewise linear graph in R2 which satisfies these three conditions is a tropical curve. So it's totally combinatorial definitions. There is no algebraic geometry behind so far. Okay, so you can check that in these examples, now it satisfied the definitions. So you have the balancing condition at each vertex, and these two, which is close to an edge on this tropical cubic, okay, now it's the weight of this edge. Okay, so now I have a vocabulary which is very similar to the one I have in algebraic geometry. Okay, I have a curve in the plane, I have degree, and I have almost anything I need to count curves as I did previously. Now I need to know what is a rational curve. So a rational curve here, for tropical curve, I will say that it is rational if I can parameterize it by a tree. So here we see that we have two kinds of curve. So the line and the conic, they are trees. The last one also with the weight of with the age of weight 2 is a tree, and the three others seem to have a cycle. Okay, but the blue one here at the bottom, okay, it's not a real cycle because we can resolve it. Okay, it's two branches that cross transversely. So if you remove it, okay, then you obtain a tree. And the two others, so the last one of the first line and the first one on the second line, so you have a cycle that you cannot resolve. So this, you have an elliptic curve, if you want. So you have a cycle. So a rational curve, a rational tropical curve, is a curve that you can parameterize with a tree. So here, okay, I have 4 rational curves among these 6 tropical curves. Okay, so I know what is the degree of a tropical curve, what is a tropical rational curve, so let's count them. Okay, so let's play the same game as before in the tropical setup. So I take 3D minus 1 point in R2, and I look at the tropical rational curves of degree D that pass through all these 3D minus 1 points. Okay, so let's do it for small degrees to see if it has something to do with the algebraic world we started from. Okay, so far here it's just a combinatorial game that have no reason to be related to what we did with Gromov-Witten and Welchargé invariance. Okay, so D equal 1. Again, it's the same question. How many tropical lines pass through 2 points? And so if you take these 2 points, it's easy to check. So a tropical line, it's a very easy object. It's easy to check that you have 1 tropical line. Okay, so let's do next case. Degree 2. How many tropical conics pass through 5 points? So here are 5 points. You have 30 seconds to find all tropical conics through these 5 points. Okay, I give you the answer. So 1, and here it is. Trust me, there are no others. Okay, so 1. This is what we had at the beginning. So now we can be confident that we have something. So let's try degree 3. Remember, it's the first non-trivial case. Okay, so degree 3. How many tropical conics? So remember, So remember that the number of complex curves was 12 and the number of real curves was 8. Okay, so now here is a configuration of 8 points, and here are all the tropical rational cubics for these 8 points. Trust me, there are no others. So what is fine with tropical geometry is that, so it's just a piecewise linear problem. So you can apply the nice strategy that we had for lines. If you have 8 points in the plane, your computer can compute all tropical cubics that pass through these 8 points. But okay, so here there. So let's count them. 1, 2, 3, 4, 5, 6. We have 9 of them. So that's bad news. So maybe tropical geometry was useless. Let's try to count them in a little bit in another way, maybe a smarter way. 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah? It works. And let's try another one. 0, 1, 2, 3, 4, 5, 6, 7, 8. Great. So you see that on this picture, I found again the number 12 and the number 8. And it's not a joke. This is really how one should count. So, at least, so one should not count tropical curves. 1, 2, 3, 4, 5, like complex curves. Remember, we were counting complex curves like that, and already for real curves, some curves were counting with +1, some other with -1, and here it's the same. A tropical curve, you have to count it with some multiplicity. So it's always, so you have one complex multiplicity, and here they are. So the first one has complex multiplicity 4. That's why I started to count at 4, and all the other ones have complex multiplicities 1. I will tell you what is this complex multiplicity in a moment, but it's a totally combinatorial thing. So if you have the tropical curve, you can compute its multiplicity easily. Okay, and you also have a real multiplicity. Yes, so the sum is 12, and you also have a real multiplicity associated to each tropical curve, and so in this case, so the sum is 8. Albin? Yeah, and you see that, so the real multiplicity of the first one will be 0, so which explains why if I start to count at 0, I obtain 8. Okay, and this is a general theorem by Michalkin, so in 2004, that if you count tropical curves with a complex multiplicity, you will obtain the corresponding probability invariance, and if you count tropical curves with a real multiplicity, you will obtain Velcharget invariance. So again, that's a really great theorem, because it's not clear from the beginning that these combinatorial objects have anything to do with algebraic geometry. Okay, and what is this multiplicity? It's easy to define. So the multiplicity of a curve, so over the field K, so here K is either C or R, so it's just the product over all vertices of the curve of the multiplicity of the vertex. So now I have to define you what is the multiplicity of a vertex, of course. So here it is. So a vertex will be trivalent. And so you have 3 vectors, okay, 3 primitive vectors, v1, v2, v3, like in the balancing condition, and 3 weights. And the complex multiplicity is just this, so you take the absolute value of w1 times w2 times the determinant of the 2 vectors, v1, v2. Okay. At least, so the formula is explicit, and it's easy to compute. And the real multiplicity is also given by this easy formula. So if the complex multiplicity is even, then the real multiplicity is 0, and if not, it's -1 to some power. Okay, so here what is important is that it's very explicit and very simple. And then you get this Michalkin theorem. But now, something... so another surprising fact arose in this story some years ago, and that are called tropical refined invariants. So here I wrote again the definition of the complex and the real multiplicities, and Goethe noticed in 2011, more or less, that there is a natural polynomial, or Laurent polynomial, that interpolates between these 2 numbers. So for each vertex, you take this rational function. So it's Laurent polynomial in Q to the 1/2. So this is the quantized, so the quantum number MC of V. So this is something like a physicist likes to do. They have a natural number they consider is a quantum part, which is this. Okay, so you have this, and then you can plug Q equal 1 to this rational function. Okay, and then you find the complex multiplicity, and if you plug if you plug Q is equal -1, then you get the real multiplicity. Bon? Okay, so why is it interesting? Then it's interesting because we count now tropical curves not with integer, but with some polynomial multiplicity, and the result is that if you count tropical curve with this multiplicity, you obtain something which does not depend on the points, the 3D minus 1 points you choose. So that's very intriguing. And this polynomial that you obtain, if you plug q equal 1 in this polynomial, you get the Gromov-Witten invariance, and if you plug q equal to minus 1, then you get the Welchanger invariance. So here are some examples, maybe, of... okay, so I computed the first Goethe invariance, so up to degree 4. So here they are. And now there is a natural question that arises. What do these quantum invariant, tropical refine invariants correspond to in the algebraic geometric world? So here we see that, so first we introduced tropical geometry to solve a problem that was coming from algebraic geometry. But now there is something which seems indicates that we have to go in the other direction. We observe this tropical refine invariants only tropically. We don't know if they correspond to anything in the classical algebraic geometry. So no one knows, so this is a very nice problem if you want to find a problem to solve, and many people will be very happy to have an answer. So far there are only some partial explanations in a series of works. So in these explanations, they shed some light on one aspect of the problem. Okay, so it seems that there is a big theory which is behind each of these work. Just shed some light on one facet of this problem, but all these explanations seems to be totally unrelated so far. So means that this global theory which is behind, so far it's completely under construction. Okay, so that was for the tropical part. Now I would like to end maybe to go back to classical geometry and to give some generalization of the problem we started with. Okay, so we started with a 3D minus 1 point in CP2. And how can we generalize it? So there is, so CP2 is just an instance of an algebraic surface. And we have many other algebraic surfaces. So here we can replace CP2 by a rational algebraic surface or a rational symplectic variety of dimension 4. These are two points of view. And so the degree here, which was a number in the case of CP2, should be replaced by some homology class that or element of the Picard group of X. And 3D minus 1 now is replaced by the first chain class of X times D minus 1. And when we count curves with this generalization, we obtain the Gromov-Witten invariance of X. And over the reals, we can also enumerate real curves, and for this we need some additional data. So we need a real structure on X, okay, like CP2 and RP2, and also I need to fix some connected components of the real part of my surface where I choose my points through which I will make curves pass through, and where to count the solitary nodes. And when I count curve in this way, I also obtain something which is invariant, which is called Welchanger invariance. So the original Welchanger invariance took place in this more general setting. Okay, so some example of Hermione varieties. So we have CP2 that we already talked about. We have CP1 cross CP1, which is an also very nice rational surface, and CP2K, K, which is the blow-up of CP2 in K points. So in algebraic geometry, there is a way of constructing an algebraic variety variety starting from, okay, we have a way to construct an algebraic variety starting from an algebraic variety which is called the blow-up. So when you have an algebraic surface, you can blow it up and it gives you another complex surface. Okay, and more or less these are all algebraic surface we are interested in this story. Okay, and what kind of real structure can we put on it? So in CP2 there is the complex conjugation, and so the real part is RP2. Okay, so this is the case we dealt with before. And CP1 cross CP1 already it's an interesting case. So CP1 cross CP1, this is just a quadric in the 3 space. Okay, so it's a given in the 3 space. It's the zero set of an equation of degree 2, and we know the classification of quadric in the 3 space. Okay, the real quadric. We have at least 2 different real quadrics. So the first one, which is a hyperboloid, and with this equation, and the second one, which is the quadric ellipsoid in the 3 space. And so each time the complex surface is always CP1 cross CP1, but we see that it can have different real structures. So on the same space, you may have a lot of real structures. And okay, so in the first case, the real part is homeomorphic to the torus S1 cross S1, and the other one, so the real part is a sphere. Okay, I gave you the 2 conjugation for this, and we also have real structures on the CP2 blown up at k points, and okay, here it is. So it's given by also a very explicit equation. So you take k, maybe 2k, not k. No, k, but k is even. So you take k real numbers that are all different and take this equation, and the real part will be k over 2 spheres. Okay, and here the complex conjugation is just the restriction of the complex conjugation of x that comes from C3, where this surface lives. So here are the examples of varieties where I will take some points, count some curves, count some number of solitary nodes, and okay, so what is the state of the art so far? So about Gromov-Witten invariance, everything is known. So they all have been computed. So first by Kontsevich, and his work has been generalized to all other surfaces. So by Goetsche and Pandaibon, so rational surfaces. So this was in the 90s. But for well-charged invariance, so we know there are a lot of works on this invariance, but still there are a lot of works to do. So, for example, there have been computed in Del Pezzo surfaces, which is a class of algebraic surfaces, which is very, 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 very important. So, in numbers of work, and so one of them was in collaboration with Lucia and Aubin. And okay, so maybe I will not make the enumeration, but. So recently I could reduce the number of this computation to the case when the real part of x has at most 2 components. So I would like to explain a little bit how it works. So as I said before, over the complex numbers there will be one construction tool for rational surfaces, which is called blow-up. Okay, so you start from CP2 or CP1 cross CP1, and you blow up, and you obtain everything. More or less. Over the reals, you have another construction tool, which is called which is called surgery along a real Lagrangian spheres. I will try to explain. Okay, so you have 2 construction tools to reduce to finitely many surfaces. So here, with blow-up and surgery, we end up with only 3 cases. So I think it's CP2 and RP2, and CP1 cross CP1 with any real structure. So it's only two cases. So that means that if you are able to relate the Weltschage you're interested in for surfaces which differ by blow-ups or surgery, then at the end, you can just work on CP2 and on CP1 plus CP1, and you're done. So you have to compute them on 2 surfaces. Okay, so what is a surgery Lagrangian sphere, along a real Lagrangian sphere? So it corresponds to degenerating the surface to a nodal surface. So let's look at what happened for quadrics in P3. So remember, we have this hyperboloid and the quadric ellipsoid, but now the ellipsoid goes by infinity. Okay, so it's still a sphere, the second one, but which intersects infinity. And between these two, there is a singular quadric. So now the parameter t in the equation is equal to 0. Okay? And also we can pass from the ellipsoid to the empty quadric by a singular quadric, which is just given by a point. And in each of this case, we see that the degeneration, so when we go from Q1 to Q minus 1, okay, what we do, we contract a sphere S, which is called the vanishing cycle. So here, this sphere, in the case of when we go from the ellipsoid to the empty quadric, is easy to see, is the sphere. Okay, but it also presents, but maybe it's not so visible in the first situation. So when we pass from the hyperboloid to the ellipsoid, okay, so now the sphere lives in the complex part of the surface. So we don't see it on the real picture, but still it's here. And the thing is that each time on a surface you can find such a sphere, which is a Lagrangian sphere, a real Lagrangian sphere, you know that you can degenerate it to some nodal surface and then change the topology. And this operation is called surgery along a real Lagrangian sphere. So to know if you can, so this is the local picture on a surface, so to know if you can change the topology, so to pass through from some tube to some 2 disks, okay, you just have to look in your surface to these Lagrangian spheres. And this is a bit easy. And so this is the second construction tool we have in the real algebraic geometry. And then there is, okay, so for example, this is what happened for this the last type of surface I gave you, okay? So between 2 spheres, you have one of these Lagrangian spheres, okay, between the 2 real spheres, and how you can draw this degeneration. So remember that we have 2 numbers, a to 1 and a to I plus 1, okay, that are supposed to be 2 real numbers, then they come together and then they become complex conjugated. And this is the picture you see on the real side. Okay, and the theorem is that there is a formula that explains you how to compute Weltschage invariance of y out of those of x. So what are y and what are x? When you do such a surgery, the Euler characteristic change by 2. So the one with the least Euler characteristic is called x in this formula, and the other one is y. So here, I was kind of surprised when I saw this formula because it's very simple, but the proof was a kind of tedious computations with binomial coefficients. So in a sense, I still don't know why this formula is true. So if someone could help me to understand this result, that would be nice. And okay, so thank you. I think there is one last. Okay, no, but it's already too late. So there are lots. Okay, just to say that there are a lot of future directions of research in this kind of problem. So this was a kind of list, but so if you're interested in this kind of subject, there are a lot of things to do. You won't get bored. Okay, thank you very much for your attention.
¿Hay preguntas?
So your last theorem looks very much like Riemann-Hurwitz theorem, like Riemann-Hurwitz formula for Riemann surfaces. Is it inspired on that?
You mean this?
When you have a branch covering of a Riemann surface to you have the Riemann-Hurwitz in terms. Is this some?
No, it's one dimension higher. But, no, it's not so related.
¿Otra pregunta? ¿No? Bueno, pues le damos las gracias a Erwan y les recuerdo que tenemos un concierto de jazz ahorita aquí mismo, así que no se vayan. ¿Y te caigo? Y te entrego tu...